My name's Truman. Let's talk about magnets. Magnets are super cool. They can defy gravity, they attract stuff from long distances, and they're used in anything from transportation to smartphones to medical supplies. But not that many people know how magnets really work. So before we get into that, let's have a little bit of fun and explain the history of magnets. So there's tons of stories out there about where these magnets were first discovered, but the most prominent story is of a farmer in ancient Greece who was walking his sheep one day, as one does, and he was shocked to find that the nails in his shoes and the metal tip of his staff was being stuck to this big black rock. So he dug it out, did some experiments, and found that it also attracted other metals, and so they named it magnetite because the farm was in this little city just north of Greece called Magnesia. Now, they did a couple of tests with this magnetite. They used it for compasses, medical rituals, and stuff like that, but they didn't really know what was going on. Thankfully, we live in 2020. There's been a ton of research on magnets, and we do know what's going on. So the reason why these little rocks are so magical and can attract metal objects from a distance is because they generate something called a magnetic field. Now, a magnetic field is an area around the magnet where the magnetic properties can be felt. I just said magnet like 10 times right there. And they are caused by the movement of electrons. Wait, that's it? That's it?
That's it?
That's it? Yeah, that's it. Just the movement of electrons is all you need to create a magnetic field. Okay, well, if I just take a wire and move some electrons through it, is that a magnet? Yep, that's called an electromagnet, but we'll talk about that later. First, we're going to answer the obvious question. So if a magnetic field is created by the movement of electrons, then how do you explain these rocks? Because they're not plugged into any outlet or anything like that, and I don't get shocked when I touch them, but they still stick to my fridge. So what's going on? Where is this movement of electrons that you're talking about? Okay, you make a good point. You don't have to plug in a magnet to make it work, but that doesn't mean that there's no movement of electrons. You see, if you take any substance on Earth pretty much, and you zoom in, what are you gonna find? You're gonna find a bundle of protons and neutrons surrounded by these moving electrons. Now, each of those moving electrons creates a magnetic field, and those quintillions upon quintillions of tiny magnetic fields add up to be one big magnetic field. Okay, well, that raises a different question. If every substance is made up of protons, neutrons, and moving electrons, then how come everything isn't magnetic? How come when I throw this giraffe, it doesn't stick to the fridge? Well, to understand that, we have to understand poles. Now, if you've ever even heard the word magnet, I'm sure you're aware that each magnet has a north and a south pole. And if you've ever been to a second grade science class, you've done the experiment where you take two magnets, and if you try to put their like poles together, for example, a south pole and a south pole, they will not connect. They'll repel each other. But if you take two opposite poles, for example, a north pole and a south pole, try to stick them together, they'll connect. Now, to explain this, let's go to the whiteboard. Now, if you'll take a look at these pictures, you'll see that a magnetic field is directional. It always goes from the north pole to the south pole. So, if you look right here, if you try to put two north sides of the magnets together, then their magnetic fields are in opposition and they repel each other. If you try to put the north end to the south end of another magnet, then the electric fields are in harmony and they will stick together. See, it's not that hard to understand, but we still haven't answered the question of why all things aren't magnetic. Now, if you'll think back to your high school or last semester chemistry classes, you'll remember that all of the electrons travel around the nucleus in what are called shells. Now, some elements, such as those on the borders of the periodic table, have filled shells, meaning that the electrons orbit equally in all directions, so the currents generated cancel each other out and generate no net electric field. Additionally, these electrons come in pairs whose poles are aligned in opposite directions, further canceling the magnetic effect. In elements with only half-filled shells, all the elements are unpaired and their poles are aligned in the same direction, and that magnetic field is produced. Thank you, Miniphysics, for that awesome video. Now, it's the congregation of all of these tiny magnetic fields that makes a substance magnetic, and if all of the fields are in alignment, we call that substance ferromagnetic, from the Latin word for iron, ferrum. Okay, final cool question that I bet you've never asked. Where do we get magnets? Do we just mine them out of the ground, or is there a special volcano that we have to get them from? And also, I thought that magnets were made from iron and nickel and stuff like that, but if I were to just take a normal piece of iron and nickel, it wouldn't stick to my fridge. So what do you do to turn a piece of iron into a magnet? Now, if you take a chunk of iron, you will find tiny magnetic fields inside of it, and they will be in alignment, but certain parts of the chunk of iron will be in line with other parts. It's kind of confusing, so there's a picture in the textbook that explains this pretty well that I'll put right here. Now, each one of these little areas is called a domain, and as you can see, these domains point in all kind of different directions, and it ends up that these domains cancel each other out and make the piece of iron not magnetic. So if you want to take a normal piece of iron and turn it into a magnet, you have to somehow break the borders between these domains so that all of the magnetic fields can align in one direction. And this really isn't as hard as you think. Turns out that heat is actually pretty good at breaking the borders between these domains. So if you just take this piece of iron, place it in between a magnet, and then apply heat, the heat will break the borders, and then the magnet will align the poles in one direction, and boom, you got a magnet.
Isn't there an easier way?
Oh yeah, there's those electromagnets that we talked about earlier. So pretty much a magnetic field is caused by the movement of electrons. So if you take a metal wire, run a current through it, you got a magnet. But the cool thing about electromagnets is that you can make them really big, really powerful, and by flipping on and off the power, you can turn on and off the magnet. It's these big electromagnets that are responsible for some of the really cool stuff we have today, like MRI machines, or my personal favorite, the maglev trains. If you've never heard of these maglev trains, they're super cool trains that you can find in Japan and I think Germany. There's only like a handful of them in the world, but they use magnets to lift the whole train a couple of millimeters off the track so there's no friction, and they can go upwards of like 400 kilometers an hour. Now, one way they do this is the obvious way, where they just use like poles that repel each other and push the train a little bit off the track. And there's another way they do it where they have opposite poles, but one is on top of the other, and they keep turning this one on and off so the train constantly is attracted and then falls, and it just like hovers there. That's just one example of the many cool things that you can do with magnets. They're honestly so cool and my favorite things to study, and I hope I helped you guys understand a little bit more about them today. Thank you guys for watching, and have a fantastic day.